So in previous videos, we have analyzed in great depth the setup of a typical distillation column. We have our condenser up top, our reboiler at the bottom, and we also have a feed at some stage that falls in between the two. What we haven't discussed yet in detail is how these stages are set up, and especially as I draw this out, how our weir, which is this kind of wall that contains our liquid, is designed, and how this design aspect actually drastically changes the entire the output compositions of our products. So the design of this weir is defined by something called the Francis-Weir formula. Weir formula. And the Francis-Weir formula takes into account a number of geometrical arguments, some experimental data relating to the discharge from the tray, as well as gravity effects and so on and so forth. So this is a very important thing when designing a distillation column. What ends up happening is that as you collect liquid as it flows down from your condenser, I'm going to just draw an arbitrary amount through here. Of course, you're going to have some vapor that'll bubble in through the bottom of your tray. That'll be from the stage below. But what I am looking at is this amount of liquid that is no longer contained by the weir and thus is prone to overflowing and going down into the next tray. This is what we will define as the molar holdup. Molar holdup. And this property is crucial for determining our molar compositions as we go through our distillation column. The main factor that affects our molar holdup is the reflux ratio, which we have previously discussed is the ratio between the amount of liquid that we are sending down out of our condenser through the rest of the distillation column to continue the distillation process, as well as that ratio compared to the distillate leaving our condenser. So you would expect that with a higher reflux ratio, we'd have a larger liquid molar flux going through our distillation column, and thus the thickness of this molar holdup would be greater. So today we will be doing a simulation of that molar holdup, as well as determining the molar compositions of our more volatile component as we go through our distillation column. And finally, we will put all that data together into a McCabe-Deely diagram to kind of visualize how we would set up this distillation column given certain requirements. So this is just a brand new Python notebook. I've imported a number of things that we can use to help us achieve our final goal, as well as our problem statement here. So we have 13 stages, and our feed stage is going to be stage 7. We have defined an alpha, or relative volatility. We have a feed of 1 mole per second, and our mole fraction of our volatile component is 0.5, so we have equimolar mixture. We have a liquid mole fraction of 0.9 within our mixture, and we have also defined a reflux ratio for 2. What we have also defined is our molar holdups. So in each of our trays, our molar holdup is going to be 0.2. That's the fraction of our molar holdup. And our boiler holdup and condenser holdup are going to be equal, and this is all at zero flow, so before we actually get our distillation column started. So the first thing that I'm going to do is I'm going to set up our initial condition here. So I'll just call this our holdup knot, and I'm going to have this be a row concatenation. So first I want to start with our condenser, so I'll do holdup condenser, holdup not condenser. And then what'll end up happening is I'm going to set a tuple for our tray. And what I mean by that is hold Holdup, not for our tray. And I'm going to multiply this by the number of stages that I have. So we have 13 stages, so 13 trays. We want to repeat that value 13 times for our initial condition. And then lastly, I'll get my boiler in here. Okay, it just looks like I needed brackets there instead of parentheses. So now that we have this holdup, our initial holdup, you see that we have our condenser, our reboiler, and then 13 trays in the middle. And essentially what's going to end up happening is that this holdup is going to be changing over time as we get our distillation column running. So I'm going to say that we have some molar amount as we go through our distillation column setup. And this difference in our molar capacities is going to have to meet a certain requirement. So before I said that we have our Francis-Weir formula, and that depends on a number of different factors. And one of the things that we can pull from that is something called a Weir constant. So let's just say our Weir constant is 0.1 for now. So this is a constant dependent on, I guess, Weir geometries, tray geometries. And there's a whole bunch of other things that go into that, but we're not going to get into that right now. So we have some sort of Weir constant. So our liquid flow rate is going to be dependent on this Weir constant times our mdiff to the 1.5 power. And this m is going to be something that we will define later. We're going to pack that into a function, and then this m is going to be a part of that input. But essentially, this is going to be what determines our liquid flow rate. And this is something that you can look up. It's part of the Francis-Weir formula and whatnot. Unfortunately, there is a problem. So if we want a liquid flow rate, we need to ensure that we do actually have some overflow, meaning that there is a positive difference between our initial holdup and our level as it functions over time. So we can set up kind of an if statement. So first we'll say if mdiff is less than 0, then we just set that value equal to 0. There is no liquid flow coming out from that. Otherwise, we will just use the value for mdiff. So doing this should give us the right conditional for us to be able to calculate a liquid flow rate exiting the tray in question. So now that we have this here, I'm actually going to program in. Actually, I don't love this just being m, so I'm just going to call this the holdup, and this is just going to be some holdup at some time position later on. And what I'll do is I'll define an initial condition for our holdup. And this is going to be different. In fact, I'll just define this as the holdup. And this is going to be different from the molar holdups here. This is going to be the initial amount of mass added at time t equals 0. So the initial amount of moles that is added, and then that's when our distillation column is going to start running. So this holdup, I'll say, I'll go np.full. This is going to create a full array depending on the size and the value that I want it to be. So I'm going to go n plus 2 to account for our condenser and reboiler. And I'm going to throw it with our problem statement says that everything is initially filled with 10 moles. And now if I do this and I calculate L, we get the initial liquid flow rates. So if even if I wanted to, I can go mdiff. So here are our initial molar values that are present in each stage, as well as the condenser and reboiler. And then these are the liquid flow rates that are going from our trays, our reboiler, and our condenser. So I'll pack this all into a function. So I'll define a new function, and we'll call this, let's call it Holdup for now. And we're going to have some time t, and we're going to have some vector that we are going to unpack. And that vector is going to be unpacked into our Holdup, is going to be equal to that. And then based on that, it's going to calculate our mole differential, and then it's going to run our conditional and calculate our liquid flow rates. So this is a good starting point for us to go on from. So now that we've calculated our liquid flow rates, what we can do is we can go off and define our distillate flow rate, because our distillate flow rate is technically a liquid flow rate just for our condenser. So that is going to be the first position of our liquid flow array, which is notated by position 0. And that's going to be over our reflux ratio plus 1, and this comes from a mass balance I had derived in an earlier video. So this is going to give us our distillate flow rate. And then what I'm going to do is I'm actually going to redefine our initial position for our liquid flow rates. And this is simply just going to be our definition of the reflux ratio, our R times our distillate flow rate. So redefining that using this distillate flow rate that we had just calculated. So now we have a value for our distillate flow rate, and we have redefined the value for our first position in our liquid flow rate array. And this technically is the flow rate leaving that that condenser flowing into our first stage of our distillation column. So just to put a little bit more sense to that. So now that we've created an array of our liquid flow rates, we can move on to discussing the vapor flow rates for our distillation column. So first I'm going to start off by defining a desired set point for our distillate flow rate. And we'll say that this set point is going to be half the feed. So something like that. Then what I can do is first I'll start off with my stripping. So v strip. And we're going to have this equal to our distillate set point plus our distillate set point times R. If you remember, this is essentially equal to what we have down here. So this is the liquid flow rate. And basically, this is just a mass balance that we are doing here. And then we want to take into account the vapor flow rate that we have going into our system. So F1 minus Q. Or minus. This will be exiting. So we're going to say in this case that whatever is exiting our system is a positive flow, whatever is entering our system is a negative flow. So just trying to stay consistent with that nomenclature. Then we will go for our rectifying section. And this is essentially our vapor flow rate in the stripping section plus that F1 minus Q. I was just missing an asterisk in between the F and the 1 minus Q. So I think we're good now. And what I want to do here is now I want to concatenate my array. So I'm going to use the concatenate function. So the first thing is the condenser. there is no vapor flow leaving our condenser, so we're going to set that equal to 0. Then for each of the 7 trays that is above our feed tray, that's going to be set to our vapor flow rate in the rectifying section. So v underscore rect, and then times n feed, or feed n, got that backwards, gosh, there you go. And then for everything below that feed stage is going to be our stripping. So v strip, and this is going to be for every stage below the feed stage, but still adding in one more for our reboiler. So now if we take a look at shape of our L, I can't remember how to do that. There we go. So we have a 15, and then if we do shape of our V, also 15. So we have now 2 arrays of the same shape that define our liquid flow rates and our vapor flow rates within our distillation column. So now we could actually go ahead and start finding our molar differentials for each of those stages to be able to simulate over time what that holdup looks like. So now what we're going to do is we're going to start kind of putting together our molar flow rates for our liquid and our vapor. So initially I'm going to set up an array. So I'm going to name this DM. This is going to be our difference in the molar holdup. So this is going to be initially just an array of zeros that is the same size as our distillation column. So n plus 2, n is the number of trays, 2 accounts for the condenser and our reboiler. Now the first step is that we want to subtract our liquid flow rates first. These are going to be the liquid flow rates exiting each of our trays. But we realize that at the very top, the liquid that exits is not necessarily what is in our array. It is that distillate flow rate. Remember that we have the reflux ratio, so we need to account for the fact that some of that liquid is leaving as distillate, and then some of that liquid is being recycled in our distillation column. So we want to say that that first position, which is for our distillate product, is going to be equal to our distillate. Okay? Then we go off and we say something like, well, what about the one where we are feeding? What about that stage? And so for that, we will say, so our feed n. So at that position, what we want to do is we want that exact point where we are adding our liquid feed to just be equal to F. Now, one thing that you might see in all of this is, well, we have the liquid mole fraction of the feed is 0.9. Shouldn't we be accounting for that over here when we kind of append that to our array? And the answer really is no, because, well, we are accounting for the fact that we have vapor that is flowing up into a tray. So we have some mole of vapor, and that amount of vapor is also leaving our tray. So there's going to be some mass diffusion, but the amount of moles of vapor entering our system, the system being a singular tray, is going to be equal to the number of moles of that vapor leaving that tray. That's kind of the thing that it's kind of the big assumption that we are making here. The fact that we don't have a dynamic change in our vapor flow rates. It's an instantaneous change, whereas with our liquid flow rates, that is a dynamic change, not an instantaneous change. Otherwise, there'd be nothing to analyze. You just have a bunch of different profiles, and there's not really going to be much change in that profile over time. So that's the reasoning for that. Now, we can go off and we look at our vapor flow rates because that's also a mole, a molar quantity. So we say something like, first let's look at the vapor that is entering each of the systems, right? Or maybe exiting. Let's start there. Now, we have vapor exiting each of our, actually, So here we have, the thing we have to consider is this. In our reboiler, no vapor is entering our reboiler. It's only leaving the reboiler. In our condenser, no vapor is leaving the condenser. It's only entering the condenser. So those are the two big things that we have to kind of consider when we are coding this out. I still think we can just do it in the sense that we want to include everything except for our reboiler, which means that we are looking at the vapor that is entering each system. So that's, we are going to, oh boy, what is all that? What we're going to do is we're going to go to our vapor flow rates array, and we are going to append by addition everything except for that very first value for the condenser, because there is no vapor that is exiting that condenser. And then similarly, we want to do the same thing, except now we're going to do everything excluding the reboiler, and this is going to be vapor that is exiting the system. Or sorry, we're going to include everything except for our condenser for our vapors that are leaving the tray. And in this case, it's going to be that same thing, except we are going to be subtracting that as it is leaving each tray. And that kind of rounds out this function over here. And we can now use this function with its given inputs to give us a plot that'll plot out the change in mass, the change in molar holdup over time. So that'll be the next part. So let's go ahead and try and get a solution from this, right? So we're going to go into our SciPy integrate library, .solve IVP. We are going to use our holdup function over, we should probably define a time span for this. So we'll go t is equal to 200, and this is going to be seconds. So we'll go over that time span. Our why not is going to be this holdup, this holdup over here. That's going to be our initial. So, and we're going to take the method as read out, and we're going to switch dense output to true. Okay, so I think what's going on is that since this function and this equation have the same name, it's getting confused as to what it wants us to solve. So what I'll do is I'll just change this to like a right-hand side of a function that we want to kind of solve. And I'm going to change that here. And now, there you go. So now the solver has worked perfectly, and we can store this result and just store the solution there. What I'll do now is I'll set up a t-plot, and we'll go from 0 to t end. Let's say maybe like we want, I don't know, say like 1,000. And then we'll go, so we'll do our holdup plot equals result t-plot. So we can take a look at that. And it gives us this array of values that can be plotted onto our graph. So now we'll go ahead, we'll go fig equals make subplots. Subplots. So now we'll do a loop. So for I in our Holdup plot, we'll go I think just that. Fig.add scatter x equals t plot, y equals Holdup plot, name equals yeah, let's see what this does. And then we'll go fig.show. And let's see what it gives us. Okay. This isn't exactly what I was imagining. Okay, so the issue lied here. I have forgotten a line in my code, and this line is basically the liquid that is entering our system. So liquid enters in every tray except for the very first, which is our condenser. So we are saying that in our array, except for the condenser, we will be adding the values from our liquid array, everything except for the reboiler where liquid is not exiting, rather that is our bottoms that we are getting out of that. So now that we have done that little change, our plot looks a little bit something like this. There was a couple issues with the naming here, so this is what our final plot code should look like. And we get to see that everything over here, so this is stage 13 until about stage 7, so this is everything in our stripping section, comes down and comes to steady state. It seems like it's at around, I want to say around 7.3 moles from our initial 10 moles. Everything here, this is stage 6. So stage 0 here is our condenser. And this stage 14 is our reboiler. And all of these are our rectifying lines that come to steady state at around 4.8 moles. So got a nice little graph here to show us the molar holdup of each tray as it continues through time at a 200-second time interval. And now we can go on to the molar compositions of the more volatile by doing a very similar process to what we had done before. So I very quickly just written out this relationship between our x, y, and alpha. So we start here. Our alpha is equal to our ratio of our k's, which is our vapor mole fraction, or vapor mole composition over our liquid mole composition. We simplify it down to get everything in terms of one component. And from there, we go down and we get y alone, and we get a relationship that looks something like this. So this is going to be crucial in helping us get that XY diagram for our McCabe-Thiele plot. And we'll be using this in our code to generate our second set, or our second array for our mole compositions of the more volatile component. So we're just going to go through and we're going to modify our existing right-hand side function. The first thing we're going to do is we are going to split up our vector here. So using our np.split function, and we're going to split this into two segments, one for our mole fraction of the more volatile component and one for our overall moles. And then what we're going to do is we're going to calculate y using the relative volatility alpha which is defined up here. So that was 1 minus x plus a times x. If I'm not wrong, pull this up. 1 minus x plus a times x. Yep, perfect. Get that in there. And the rest of this actually is just fine. Except now what we're going to do is we're going to introduce this DMX. And really what I'm going to do is I'm going to copy all of this and paste it here because it's going to follow a very similar logic. So for our liquid, we want to, of course, multiply that by our liquid mole fraction. Makes enough sense. Going to change all these to DMX because we are now dealing with our new array. For our distillate, we just want to multiply this by the first value in our X array. And then we have our the liquid entering each of our trays. So we're going to multiply this by the mole fractions for the same set of molar flow rates. And then for this, we're just going to multiply it by our feed composition that we have defined up there, so 0.5. So that's fine. Over here is where we're going to start using our y. So this is going to be multiplied by our y for that same range. And we're going to multiply this by the y for the same range. And this essentially is everything we need to do to mess around with our DMX array. So now our goal is we want to find dx just like how we found dm. So let's just do a bit of calculus here. So if we want to do a derivative of mx, using our product rule, we have a x times dm plus m times dx. What we're after is dx here. So what we're going to do is we're going to go, so dmx minus x times dm all over m equals dx. So just a very simple calculus problem there. Oh, goes my pen. And we can very simply code this in to here. So our dx is equal to our dmx minus our x times dm all over our m, which is this part here, over m. And I've changed this to m. I can't remember if I mentioned that. I changed this to m as to avoid confusion with our holdup up here, just making sure that that stays discrete. So what we're going to do is we're going to run a return a row concatenation of our dx and dm. And that should be this function finalized now to give us both our molar holdup and our molar holdup of the more volatile components. So before continuing on, like how we had this initial holdup over here, we're going to have to do a very similar thing for our x. And we have that because we have an initial set for all of our for our feed. So we're going to go np.full. We're going to make it the size of our column. And we're going to use z as our initial state because that's what's being fed into our distillation column. So now that we have that, what we can do is we're going to give it a concatenation of our x and our holdup. And then we're going to have to split this result into 2 to get our individual plots. So we're going to have a holdup plot, and we're going to have an X plot. And I believe we can just copy this and change it for our X. And I'll go row equals 1 and calls should be rows. Calls equals 2. So we can have these side by side. And now we're going to go X plot and X plots. So our X is still T plot, our Y is not going to be X plot. Let's give it a run. I think I just need a I need a specify where I want this. So we're going to have row equals 1, call equals 1. And then this is going to be column 2. And there we go. Now we have these side by side. This is our moles of the more volatile component over here. This is our overall molar holdup for each stage. So we have these nice and pretty plots now side by side. So one thing to note here, and it won't really affect what we've done with these graphs, but it's definitely noteworthy. The issue with having this like this is we're not specifying where we want our split to be. So in order to specify that we want to split our x's and our holdups, we can set our axis equal to 0. And again, it doesn't really look like it changes much here, but in the case that this function would split it improperly, we would get really wild results here. So it's always good to just have that on. Now the last step is to generate our McCabe-Thiele diagram. And we're going to start off by looking at, so let's look at our result, which is our differential equation solver here. So we see that we have our time spans, and we also have a select amount of y's. So let's look at our y. Let's see the shape. So we have a 30 by 17. So our 30 is half of that is going to be our x's, and half of that is going to be our molar holdups. And 17 is the amount of time steps that our differential equation solver chose to solve our function over. So what we really want is we want everything from our solutions for our y, and we also we want the very last time step that we have here, and we're gonna split this in half. So np.split. I'm going to split this in 2. We'll just do -1. That should work. So we have all of these is our compositions, and all of these is our molar holdup. So now I'm going to store this. So we have now our x's and we have our m. So this x's is of course our mole fraction of the more volatile component, and then our m's is our total amount of moles in each stage. Based on those x's, we can get our y's, and that is going to be, well, actually that exactly, that's our relative volatility. I believe it should be, or double check myself. Yeah, alpha x. So alpha times x's. Did I do that up here? Where's my y's? Yeah, so alpha times x over 1 minus x plus alpha times x. So we have our y's. And now what I'm going to do is I'm going to introduce my x's for my McCabe-Thiele. And what I'm going to do is I'm going to have to set up another array. So np.array. So my first term is going to match my x's. So I'm going to take the 0 position from that. And then what I'm going to do is np.repeat. And this is going to repeat the values that I specify for the set amount of times that I specify. So I'm going to repeat everything in my x's. So everything in between, so from 1 to -1. So 1, 1, -1. I'm going to repeat that 2 times. And then finally, I'm going to keep my last value the same. I see my mistake. I shouldn't have done an array. This should just be a row concatenation. And then these can still be brackets. Come on. Perfect. And now our y for the McCabe-Thiele is a bit more straightforward. That's just going to be equal to our y's. We're going to go np.repeat our y's. I'm going to repeat the entire thing twice. So now if we look at our x MC and our y MC, so you see that for our x, we start up at our distillation end. So this is our distillate composition. And then what happens is that we go over and we hit this x value. However, our y stays the same. So this is our first step over hitting our equilibrium line. And then we're going to drop staying at the same x. And then since they're offset, we're going to create our staircase in this way. So realistically, this is our McCabe-Thiele staircase. We just have to go ahead and plot it out. So let's go ahead and make a subplot. Make subplots. And what I'm going to be doing here is first I will set up my range that I'm going to be plotting over. So I'll set my equilibrium x, np.linspace, go from 0 to 1, which is our range of compositions that we can have. We can say we want 100 evenly spaced values in between that. Our YEQ is actually going to be this here. Instead of using x's, we're going to use XEQ. So go XEQ here, XEQ. Now, it's as easy as just adding the scatter. So our x equals our XEQ, our y equals our YEQ, and mode equals lines. I think it automatically goes to lines, but I will just specify it. So here is our equilibrium curve. Then we repeat the same. And this time we use our McCabe-Thiele values. Oh. That doesn't seem exactly right. Because this staircase should be under our equilibrium line and then bounded by our x equals y line. So if we analyze back this array, we see that we should have agreement between these two data points, these first ones. What ended up happening, though, is we started going over prematurely when we should be going down and then over. So the way to fix that is I'm going to repeat the first the first value, which is technically, so this is indexed as 1. This is indexed as 0. So we need to repeat this index 1 and then start from there. And give it that. Okay, now that should actually give us the staircase. Beautiful. So now we can go ahead and we can do one last thing, which is going to be graphing our x equals y line. 0, 1, 0, 1. Right. So now we see we have our McCabe-Thiele diagram. What isn't graphed here is our rectifying Q and our stripping lines. But we've done that in a previous video. I'm not going to show that here, but we now have a staircase which will define the design of our distillation column with these given inputs based off of the calculations we have made here.